quantum technology is very significant, very magical aspect of physics. And after many years, a prize has been given in this field of quantum science. Classical physics is the basic laws of motion, of velocity, of how things move, how force is applied, all of that which we study, that is your classical physics. That they have brought this understanding of quantum science to the macroscopic level. It can behave like a particle, the properties of particles will apply, but it can also behave like a wave. This is something which was very astonishing. Energy at restricted levels, at specific levels, in specific packets. Hello everyone and welcome to our discussion on the Nobel Prize for Physics 2025. We are going to quickly talk and understand this new amazing development which has taken place. So the Nobel Prize in Physics, I'm sure you all know about the Nobel Prize. So Alfred Nobel, after his name, this award has been created, and he says, this Nobel Prize in Physics is to the person who made the most important discovery or invention in the field of physics. So we are going to see what is this year's most important invention or discovery in physics. The award this year has been given for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. The term to pay attention to here is quantum. Okay. So here, this quantum technology is very significant, very magical aspect of physics. And after many years, a prize has been given in this field of quantum science. So because of that, this particular Nobel Prize is very significant. It has been given to John Clark, Michael Doverit, and John Martinez. So all three of them, they worked together. So John Clark was the main professor. These people, they joined him as his colleagues, and they have all conducted an experiment which has proved microscopic effects of quantum science. Let's first start by talking about what exactly this quantum is, and then we'll come back to the idea of the discovery. So quantum science, quantum mechanics, quantum physics, before we had this, we have classical science, or we can say classical physics. Classical physics is the basic laws of motion, of velocity, of how things move, how force is applied, all of that which we study, that is your classical physics. But quantum mechanics is mainly to describe things that are very small, such as atoms and electrons. When we keep a particle, we keep a substance, and we keep making it into smaller and smaller, smaller and smaller segments till the time we reach the level of the atoms, the particles, the subatomic particles, that means particles within the atoms like electrons. When we reach that level, what we found was that the substance now, or the thing now, does not really behave like a particle. Okay, like the larger particle and the laws of force and velocity, they will not exactly apply in that small size. And this is where quantum mechanics comes in. This is governed by some different set of rules, some different set of principles, and that is what is quantum mechanics, quantum physics. In this, the main idea which is there is that the particles can also behave like waves at that very small level. So we have what we understand as wave particle duality. It can behave like a particle, the properties of particles will apply, but it can also behave like a wave. This is something which was very astonishing. And this is what could not be explained by the rules of classical physics. That is why it was understood that to accommodate this idea of the wave behavior of matter, they have this special concept of quantum mechanics. Here, further, they're saying everything happens in steps, like electrons in an atom will jump different energy levels. We'll talk about this in detail. And here, there is an issue that you cannot predict everything exactly. There are chances and probabilities based on which these things will work, that it could happen or it could not happen. And this kind of a mystical element in science is what quantum mechanics is all about. And this is what this latest research or experiment of these three scientists are going to prove. The word which we read here, discovery of macroscopic quantum mechanical tunneling or energy quantization. Now, understand this term macroscopic. Let's focus on this. What we've said is that quantum science is about matter in its most smallest size, small particles, atoms, parts of atoms, subatomic particles, electrons. So it's their behavior which is what is a part of quantum science. But these three scientists have done something very amazing, that they have brought this understanding of quantum science to the macroscopic level, not in that small finite level. This was always a question in science. When scientists were studying quantum technology, quantum science, they always thought that what would be the largest size up to which these quantum properties will exist, and what is the dimension where only classical physics will apply. So now this particular experiment has taken that leap where macroscopic quantum mechanics makes sense, has been experimentally proved in an electric circuit. There are two concepts here which they are mentioning. So one is tunneling and second is energy quantization. We will talk about both of them. But let's just appreciate for a moment the brilliance of this particular development. What it has done is that it's the physics Nobel Prize here, has brought quantum properties on a human scale. So earlier, like in this image, if you can understand what they're trying to show, this is exactly from the Nobel Prize's websites. So they've shown that quantum technology, quantum laws, quantum science was known at the atom level. This is the standard description of how an atom is. So this center thing is the nucleus, and around this, the parts which are shown, they are the parts of the electrons. So earlier we knew about quantum science at this level, but the experiment here or the development here has brought this from the microscopic level to the macroscopic level, to the levels which are better perceived by us. And in this, they've done it through an electrical circuit. Okay, that's the description here. So that transition of microscopic to macroscopic makes it possible for us to use quantum technology further, explore its advantages, explore its properties, and it can be applied to real life applications. Let's understand the two key ideas here. The first one was tunneling. Okay, this is going to be really fascinating. See, tunneling refers to passing through barriers that should actually be impossible to pass through. The simple example of this is what classical physics explains. So this is a boy. He's throwing a ball at the ball. Okay, so if I start throwing ball at a particular wall, the ball is going to come back to me. I'll throw the ball comes back. This is what we understand in classical physics. Tunneling is a possibility when the boy throws a ball, there's a wall in between, but the ball goes to the other side. Just think about it. This would happen if this ball somehow makes a tunnel through the wall and then goes to the other side. And this can happen in quantum science. Depending on how big this wall is, how big the barrier is, uh, they can actually identify and understand that how long will this kind of possibility of tunneling take place. Okay, so this is uh, seen in actual places, in actual events. Like one example of alpha decay we are going to take. See here, this will, of course, the ball going across a barrier, that might seem a little less possible, but I'm sure you all will be able to understand this. This will make more sense. So there is a nucleus, okay, there is a substance here, this is an atom, it has a nucleus, and there is a barrier around this. But if there is radioactivity here, or let's say basic aspect of decay, so there is an alpha particle which can be released by this nucleus. Okay. And this alpha decay, which will happen, the radioactive decay which will happen, creates this possibility that a part of this nucleus, if there is an alpha particle coming in, right, it is coming from this nucleus only, right? It's been created in this. This is a part of this structure. So this can pass through the barrier and go to the other side, right? So this radioactive decay would be an example of tunneling. So this tunneling is what is possible in quantum science, and this tunneling is what experimentally they have proved also in that circuit. We'll come to that circuit also, what actually happened here. Okay, so tunneling means when something is ideally not supposed to pass a barrier, but it does. Tunneling refers to passing through barriers that should actually be impossible to pass. The second aspect is the aspect of quantization of energy, something which was mentioned here also. So in energy, there is this idea that everything happens in step. If electrons have to jump between different energy levels, they are going to do that in steps. Now let's see what this would mean. So here also we've taken a very good example of a ladder to explain the whole idea to you. This is quantization of energy. Now what this means is, if energy has to be created or emitted from a particular place of, or like they said, the electrons have to jump energy, that energy is not like a ramp. A ramp is like a continuous entity, a continuous structure. You can exist in any of these levels. So energy is not continuous. Climbing this ramp, you can stop at any point, right? You can stop here, you can stop here, you can stop here, you can stop here, wherever you want. A ramp does not have discrete or specific values. So energy will not use this pattern. Energy is there in packets. There are different packets here, just like the ladder. Transmission of energy, creation of energy, electrons getting energy, that is going to happen like how things work in a ladder. And this means that energy is quantized or restricted to specific levels. This is like how climbing a ladder must be done using rungs. So these are the rungs. Okay, these steps of the ladder, they are called the rungs. You cannot step between the rungs. Okay, so if you are at this energy level, the next level is here. Up, you have no possibility of going anywhere in between. Like in the ramp, which was continuous, you could go at any level. Here, you have to jump to the next level, then the next, then the next, then the next. So energy here is quantized. Energy here is in packets. That's how energy is released. So this is another quantum property, which we say quantization of energy, or energy at restricted levels, at specific levels, in specific packets. Okay, let's talk about the specific experiment which these scientists have worked on. And this is an old experiment. Interest in such kind of possibilities have been taking place in different contexts, like material science, for many years. Like 1960s onwards, these kind of experiments are there. This particular experiment also, the research based on which is now being awarded the Nobel Prize, this happened in the 80s. So let's understand this. This is the basic model of the circuit and the specifications of it. So what they have shown here is the first case is that of a normal regular conductor. In a regular conductor, electrons jostle with each other and with atoms. This causes resistance. So these are different electrons. See, for current to pass through something, for something to conduct electricity, there is some resistance. Okay, it's the electrons which are going to be aligned in a particular way that will complete the circuit and current will be created. But there is always some resistance in the material because of its composition. So that resistance they are saying here is because of how electrons would not really be arranged in one sequence. There will be some jostling between them, there will be some tussle between them and the atoms. So all of that, it's not perfect, so there'll be some opposition to it because of that, and that is what is resistance. Okay, the second case, they are talking about a superconducting state. Now, this term you should know. If you already don't know this, please understand this. Superconductor is that state of a material where there is no resistance. We usually talk about certain elements having this property where they can become superconductors, but that is normally achieved at very low temperature. Superconducting behavior would mean that current will pass in the most perfect way without any resistance. So when that happens, that is a superconductor. Okay. Now in the second case, what they have done is they have taken two superconductors. Okay, and in a superconductor, you can say the electrons are all nicely arranged, they're holding hands, they're standing in one line, right? You can see there. But in this, what they've done is they've put in a gap. Okay, they've put in a gap, and this gap is a standard term. It's called Josephson Junction. Okay, now this Josephson Junction has been known, or the experiments on such a system, they have been known for a very long time, and a lot of people are dedicatedly working on this. So you have two superconductors, in between this gap is there. So this kind of is a insulator. Insulator means which kind of opposes the passage of current. So in a superconducting state, the electrons form pairs and the current may flow without resistance. Okay, because of these pairing of electrons, you can see here, the current will flow without resistance, but there is an insulating gap which might stop the current. Okay, so the scientists here, what they've tried to do is they are working on this Josephson junction, and with superconducting material having an insulated or a gap, insulating gap between them, what they find is there is a possibility that even with this gap, so if there's no gap, there should be no current, right? There should be no current passing it. But what they observed is that the whole thing, the whole system of electrons, it would function as one large unit, and this large unit will make it possible for current to flow even without the complete sealing, even with this gap. So that's what has happened in the third stage. So a large number of pairs of electrons may sometimes behave as a single particle, and this enables the current to tunnel across the insulating gap. Okay, this is the tunneling effect, that this whole thing now is working as one entity rather than all these separate units, but all the electrons, they've aligned themselves in a way that this is now one unit, and this is like exhibiting the quantum property. And what is the quantum property? The quantum property is tunneling here. Okay, this has tunneled through the gap. It has passed current even through this gap. And that is the amazing thing which has happened in this experiment, that on a macroscopic level in a circuit across a Josephson junction, the circuit was completed irrespective of the insulating gap. And this is because of that quantum property. It was a quantum property, but now we see it at a macroscopic level. This is the amazing experiment which has happened, and it is supposed to really open us up to more such developments in quantum science and real life applications in quantum science. So there are promising possibilities that this could lead to, of course, a better understanding of quantum systems, right? With this kind of macroscopic presence and macroscopic proof of different quantum states, there is definitely going to be a better understanding, and then this understanding can be applied to different applications. The biggest one is quantum computers. Quantum computers are going to be exceptionally fast, like the calculations or the work which a quantum computer will do. A normal computer today, it will take years and years to do that one single task. That's how fast it is. Then you also have quantum sensors and quantum encryption that can be used in different areas, and there is a lot of interest in all these fields already. The only problem which has been there is that because it's at microscopic level, you find it difficult to work with it. Now if it is there at the larger scale, at that macroscopic scale, you can create those structures which will follow the quantum laws. You can make quantum chips. It's very much possible to do that because of things like tunneling and quantization of energy, which we now have proved experimentally. And there has been a lot of work which is already in place on this. Okay, like India, for example, if I particularly talk about India, we have a national quantum mission. We want to do all of this. We want to do quantum encryption. We want to have quantum sensors. We want to have quantum computers. Okay, so this is very, very significant from that part, that applications make more sense now, that it is not just limited to your understanding of atoms and electrons, but it can be applied elsewhere. So this was a discussion on the Nobel Prize. I hope you were able to understand and grasp its significance. Thank you.